and then the application.
Oh, can I make you? Oh, I'm sorry. I made you host, not presenter. I'll do that.
Oh, you got a presenter? Yeah.
Now you should have it. Did presenter come up?
Oh,
I think we should do presenter. There you go. Share application or whatever you want to do. Yeah. Cool.
So I just have a few slides here. There's not a whole lot here. There's going to be a very high-level overview, and then I think what we're going to do is after we go through these slides, I'll stick around and I'll do another presentation that's more about like a more basic kind of overview of how OBS works. So first thing is the mailing list. So all of the development on OBS happens through the mailing list, and so the way that you do that is vSwitch.org webpage. If you go to the main site, you'll see some links for all the different mailing lists. There are 4 of them. There's Discuss, which is where users go and do their, if they have user-level questions about how to use OBS. Announce is where we announce OBS or things like the hackathon. The Dev is where actually all the development happens. So all the code that goes into OBS is sent to the Dev mailing list. And then it gets reviewed by other people, and then gets axed and decide whether it should go into the code base or not. And then the Get is and then the Get is just a hook that sends things out to the mailing list, and people when patches actually get committed. So all of the development happens with Git. If people have questions about how to use Git, we can discuss some of that discussion or in the later on. As I mentioned, all the development happens on the mailing list. So there's the dev mailing list where all the code review happens. The Git mailing list is where change notifications go. All code is peer reviewed, and there's this link that's available on the Open vSwitch website, which is pretty handy, which is a web browser, or you can, with your web browser, you can look at the repository, see all the commits, browse the source code. Right. So the main parts of OBS consist of these blue boxes. So you have the OBS DB server, which maintains all of the configuration, OBS vSwitch which has the forwarding logic, and then the kernel module, which is actually is like a cache of recently seen traffic so basically when traffic comes in, it goes to the kernel module. The kernel module doesn't know what to do with it, sends it to vSwitch. vSwitch figures out, based on the configuration, what to do with it, and then updates the cache in the kernel module. And all of OBS is remotely configurable, so you can see these channels that go up to this off-box control cluster. So there's the open flow channels that communicate for vSwitch which updates the flow table, and then you have OBS DB server, which uses the OBS DB protocol to do configuration that way. And so we'll dive into all of these components a lot more in the next presentation for people who aren't familiar with all of this. So in the repo, these are some interesting files to look at. So there's a design document, and this contains descriptions of things that are maybe non-obvious about like why we made decisions the way we did. So for example, in-band control is this very subtle thing that we do to allow the switch to be able to communicate with the controller out of interfaces that are also managed. And so we have all of these sort of complex rules that are subtle implications. And so the design decision and how we came up with that are all in that design document. The FAQ is a FAQ. Ben likes to point to that a lot when people ask questions on the mailing list. It's probably his favorite file. And then there are a number of install files that describe how to start OBS in Linux or BSD, things like that. The integration guide describes how you can integrate OVS to a new platform. So, for example, there are certain keys that need to be added to the OVS DB if you port this to a new hypervisor. So, for example, if you ported it to, someone comes out with a new hypervisor, they need to support a VIP UUID to describe the virtual interface so that the central controller can know what that interface maps to. The integration guide describes how you do that, what all of the keys should be populated. And it's really about more of a convention. It describes the convention that we've come up with to update information to the central controller. The porting guide is more low level, so this would be how you actually port OVS to a new platform. And I'll have a couple slides to describe to get into a little bit of the detail of about the porting guide. But for example, if you wanted to port OVS to a switch ASIC or something like the DPDK port that we just recently did, the porting guide is a good place to look for that kind of project. And then there's this OVS-DB specs, which contains the description of the OVS-DB protocol. That's now an informational RFC. This is a little bit outdated, and so one of the things that Ben broke out as a possible task is to bring this more in line with what's actually in the RFC. When you want to submit patches, there's a file called submitting patches in the root of the repo. When you want to submit a patch, you should use get format patch. That gets it in the right format to send it to the mailing list so that we can look at it. And so each patch will be in a separate email message. Make sure that each patch that individually you don't want to break the build. So if you have 12 patches, let's say, each patch along the way should build and make check and you kind of continually build them so that at no point there's no breakage along the way. If you've updated anything related to, if it's an interesting feature that's visible to users, make sure you add appropriate man pages and the news file. The news file is actually what I use when we announce new versions of OVS. That's how I remember what's in the individual release. So if you want it noted in the release, make sure you update it in news. And then finally, you need to, in your patch, each patch needs a signed off by, where you do signed off by and then your name and your email address. And by putting that in the patch, it means that you've agreed to the developer's certificate of origin, which is described in the submitting patches. And that really just describes that you understand this is going to an open source repository and that you're giving the code away and all of that. So, but it's, you should look at that, and if you're working for a large corporation, you should make sure that they're okay with you, following those guidelines. So code layout, these are all directories that are in in OVS. So the data path contains the Linux kernel data path. So we probably should rename that at some point, but right now we just call it data path. Include has include files. Lib is a lot of common files that are used by OVS, and then we have other processes that we also use. So a lot of the common library code is in the lib directory. OFProto is the OpenFlow library. It actually contains most of the logic that does the switching. Actually, it is actually we call it the OpenFlow library, but it actually contains a little bit more than that. And then we'll get into that a little bit later. The OVS-DB contains the OVS-DB database code for both servers and clients. Utilities has the utilities for OVS, so that's where things like OVS OFKettle, vSkettle, and DPKettle all live. And then vSwitchD is the source code for the vSwitchD process, and that's sort of when you're running OVS, that's sort of the root, and then it makes use of these other files. So OVS vSwitchD does the actual switching. It has the forwarding logic, so it reads the configuration from OVS DB server. It receives packets from the data path, figures out what to do with them, and caches them appropriately. Or actually, sorry, it talks to the OFProto library. The OFProto library actually is what does the translation. Then you have the DPIF. Actually, I think I'll actually. It'll be a little bit clearer. Sorry. I think I'll work with that clear. So vSwitch this is the directories that these in parentheses are what where the files exist. So bridge is sort of the top level. When you configure something, you have bridge instances. That's in the vSwitch directory. vSwitch talks to the OF proto layer, and then the OF proto layer then speaks to sort of these two separate branches. On the left side, you have the NetDev side, which is the what actually talks to the network devices. So, for example, when you want to determine what the speed of an interface is, or send a packet out of an interface, it can use this NetDev library. And then on the other side is the OF proto library, or the OF proto DPIF. And OF proto DPIF is the actual forwarding logic. So it has the table that describes what to do with the packets. And so if you were to do a port of this, for example, we have OF proto, then you have this OF proto DPIF. OF proto DPIF makes these, explodes misses into exact match, megaflow entries that then get pushed down to the data path. And so each one of these layers you can integrate. So for example, at the DPIF Linux, this communicates with the kernel module, but you could also have, for example, if you ported this to BSD, you could imagine having a DPIF BSD interface that then communicates with the kernel module in BSD. The BSD port currently doesn't work that way. The way that the BSD library works is that there's a NetDev BSD that communicates with the network devices on BSD, and then we have another data path, which is DPIF NetDev, which is a user space data path. And so then you end up with, rather than having a kernel module that does the forwarding, you have a user space data path. And that's actually how we ended up doing the DPDK port as well. So the DPDK port, there's a NetDev DPDK, and then down here we use the DPIF NetDev user space to do DPDK forwarding. And then we improve the performance of the DPIF NetDev implementation so that it'd be sufficiently fast for forwarding packets. Is there any questions? I sort of rushed through that. Yeah.
Really basic question, but what's the difference between OF proto DPIF and the DPIF?
Right. Okay. Yeah. So each one of these are we have function pointers that so you register functions that.
Let me put the question in a different way. Where do the real ports sit? Do the ports sit?
Remote viewers, could you repeat the question?
Oh, sorry. So the question. Sorry. Could you repeat the question and then I'll.
So the question is, where does the real port actually attach to? Does it attach to OF proto DPIF, or the DPIF Linux? Where does it actually attach to? Where is the point of entry of the packets? Okay, so the question is, what's the point of entry for packets? And so in the case of when you have a DPIF, like in this case, the packets are or the ports are actually attached to the kernel module, and then the packets come through the kernel module, and then they end up as misses that go up. Now, if you were to do something like the DPDK, they're going to come up through the NetDev, and then they get handled. Then they get handled by there's a DPIF NetDev that receives them. So the ports are going to be attached in the case of like DPDK over here, and then in the case of a Linux forwarding module, they would be down in the kernel module. Any other questions?
Are these slides available?
Yeah, we can. I'll send them out to the mailing list. Sorry, the question was, are the slides available, and I'll make them available.
Suppose the packet will go through which path in this diagram?
Why don't we do that for the next topic? Because I think a lot of people are already familiar with it, and then we'll go into how all the forwarding happens in another set of slides.
I just want to know what's the difference between this one and this part, the two data paths.
Okay, so the question is, what's the difference between the two paths? And so on the right side, this is where the actual flow table exists.
Yeah.
And then on the left side is where is just dealing with network devices. And so there's sort of two different things. And then but in the case of a DPI of NetDev that you have down here, this sort of terminates, down here. There's nothing that goes further. And then the packets will be, this is what will interface with the actual hardware. Okay. And so as I mentioned, each one in parentheses contains the directory that contains the source code for each one of these modules. So we covered all of that. So integration code, that the bulk of the code is platform independent, meaning that you just need a standard C compiler. Then there's platform-specific code for various Linux distributions and Zen Server that have their own directory that contains the glue that makes them so that they work seamlessly on those platforms. And so then, and then in each one of those directories, they have init scripts and platform-specific daemons and various glue code to make it all work. There's a Python directory that has Python bindings. So many of in the lib directory, there are these C-based libraries, for example, daemons and logging and all of that. And then we also have Python ports available for most of those functions. And then there's also bindings for interfacing with OVSDB through Python in that Python directory. So if you look in the distribution, you'll see there are some examples of, a lot of times we use Python if we just need something small to sort of glue various pieces together. So there's lots of examples in the OVS code base of using the Python bindings. And then something that's really important for us is testing. So there's a test directory that has auto test unit tests. When you run make check, there are nearly 1,500 unit tests that run right now. And so this is a couple of useful flags if you want to run it. So if you run this test suite flags with a J8 for 8 jobs, then that will kick off multiple of them simultaneously, because there's obviously a lot of tests, and so some of them, if you have multiple CPUs, they can run in parallel. So that's useful. And then sometimes you'll run it, and there's one test in particular will fail. So if you use this -K argument and then specify the test, then you can limit your tests to those, which will make it run a lot faster, obviously. And so if you're going to add any new feature to OVS, please consider adding unit tests, because they're helpful and they find a lot of bugs. That's all I had. Any other questions? Okay. All right, then I think.
Yeah, so should we should break out now? Okay, so you were going to give a more deeper overview now for the people that are new. So how many people are going to stay for the deeper overview? I guess to get a sense of. Okay. So then I wonder if we should almost take these to a different room and like the suggested topics, and we can start there. What do you think? Sure. Okay. So if you're not going to stay for the deeper overview, we'll move to the other rooms. Let's see. Oh, I need to make Justin a little. So for folks on the phone, we're going to dial out for a second, and then we'll be right back. Okay, we're back. Okay. I should be good. I think that one. There you go. Yeah.
Okay. And then.
Okay.
Moving to the room.
Okay. Yeah. So anyone who wants, we're going to be in the room across the hall, and people that aren't going to stay, and we'll self-organizing.
anyone here is interested in the rest? So this is a, I thought to do is take the, because we made a decision sort of last minute that there might be good to have some introductory material. So all this is a presentation that I gave at OpenStack in Hong Kong last year. We won't go through the entire presentation because then it gets pretty deep, but the beginning slides are still relevant. One thing that this doesn't cover is the new multi-threading architecture. We can talk about that a little bit, but that's sort of continuing to evolve. So this will kind of discuss OVS as if it has a single thread. But, you know, let me know if you have any questions. Okay. Yeah, I think most people here are already familiar with a lot of the features of OVS, so I'll just skip over that. All right. So as we discussed before, there are, oh, and if there are any questions now, just feel free to ask as we go along. So the main parts of OVS are these three blue blocks, and this is for deployment on Linux. So you have the OVS DB server, which is responsible for kind of slow-moving configuration state. Then you have OVS DB responsible for, and sorry, let me see if I can mute some of these. Okay, well, hopefully won't have too many people talking. All right, so does anyone know how to make this go to the back? Okay, good. Oh, just close it? Okay. All right, thanks. All right. All right, so here, we'll just go to this. So on that block that was on the left, you have the OVS DB server. And so that's responsible for having the switch level configuration. So when you do something like you add a bridge and then you attach interfaces to that bridge, that's held in the OVS DB server. And then that's also where you configure things like where the manager should connect and where the OpenFlow connections should connect. So the configuration there is durable. It stays on disk. However, some of the, depending on the integration that was done, that can still be blown away on reboot. So for example, on Zen server, when you know, even though things are stored on disk, Zen server expects that the configuration is gone and then has to rebuild everything. So the first thing that the Zen server script do on boot up is blow away all of the configuration and then rebuild it. So, so that can be a little bit confusing because we'll say things like, oh, it's durable, but then people make configuration changes, reboot the box, and then it's gone. But that just has to do with the way that the local integration scripts are done. So the OVS DB server has, has nice database properties, value constraints. So you can say, for example, that a VLAN can only, has to be less than, 4096. You can do, weak references, meaning that you can have things linked to each other, and then if one of them, let's see, garbage collection, weak references so that you can maintain some of the references, and then garbage collection so that if you blow away things, then it'll clean itself up if there's nothing that points to them. Which actually, oh yeah.
When you say persistence on disk, is it a change comes in and goes down, and you don't respond back until it's there, or is it checkpointing?
So the way that the OVS DB server works is that it's actually a log-based system. So when configuration changes happen, it gets appended to a log. So there's sort of a known good state, and then there are a set of changes that happen, and they get replayed. When that log gets too big, then it gets compacted down into like a known state, and then we start appending other changes again.
Okay, but that's all on disk, or as the changes come in? So it's only after the asynchronous comes back up that you go to disk, or so in other words, you don't have you have what's requested, but you don't have what's committed.
So the so you're saying like when a request comes in, does it get committed to disk before we acknowledge? And I actually don't remember. That would be a question for Ben. So I suspect it does get committed, but I'm not absolutely positive on that. So I mentioned that it's log-based, so this is very helpful when you're trying to debug what's going on, so you can actually replay the log and look at what happened, which has come in handy a lot for the work that we've done at Nicira and VMware, because you have all of these things that are changing configuration, and we can look back and say, was it the controller that made that change? Was it something that we did? And so you can kind of assign some blame. And so one of the things that you can do in OVSDB is it has the ability to comment. So so they can, when you make changes, you can actually annotate the changes. And so we encourage people to do that. So for example, if you run OVS-vs-kettle, it will, when it makes a change to the database, it will copy its arguments into that comment line. And then our controller writers, for example, they will, if they're adding a VIF or something like that, or a tunnel, then they'll put in a line saying what they're doing. But if you don't, that line will be blank. And so I would encourage you to do that, because otherwise it ends up being a nightmare trying to figure out actually who made the change. So it uses this OVSDB protocol, which is available as an RFC, informational RFC, and that's what we use. That's how you make changes to the OVSDB. So the remote manager uses OVSDB if it wants to add a tunnel interface. It uses OVSDB to do that. And then if you run OVS-vs-kettle commands, that's just a local client, OVSDB client, that then actually makes a database call out to OVSDB server. All right, and so, yeah, I missed. So we'll go here. So the OVSDB server and OVSDB. The question was, what do you mean by redundant? Oh, read only? Yeah, no, it's read write. So the question was, this communication channel between OVSDB server and OVS vSwitch D, is that read write or read only? And it's read write. It goes both ways. So for example, if you could run vSkettle and add a tunnel, that will happen here, and then OVS vSwitch D will be notified that there was a change to the database, and change its configuration to add that tunnel. But then there are also things like stats, or the OpenFlow port that was assigned to that tunnel will be added to the database and then pushed that way. So it goes both ways. I have this arrow that just goes in one direction, so it goes both ways. But the configuration that happens in OVS vSwitch D is not persistent. So it's persistent on OVSDB server, but any flow table changes that you make are not persistent in OVS vSwitch D.
So when the reboot happens, when you replay all the configs on the OVSDB.
Right. So the question when reboot does it replays all of the config, and yeah, that's right. So it goes back and it figures out what the state it should be in. It just replays all of the logs and then gets in the known state. It doesn't replay them to vSwitch D. It just figures out what the correct state is, and then on startup that just tells it what the correct configuration is.
OVSDB can be controlled by a controller offsite as well as a command line tool, right?
Yes.
So is there some parity which takes preference, or?
So, sorry, was it vSwitch D or DB server?
The OVSDB server.
Okay, so the question was, is there some sort of preference on who makes changes, if it's remote or local for OVSDB server? And it doesn't make a difference, because as far as OVSDB server is concerned, they're just connections that are coming in. So everyone speaks, this is over a TCP or SSL connection. OVS-vs-kettle is running over a Unix domain socket, but OVSDB server isn't aware of, it's just whatever order that they come in. But there are, if they both try to make changes simultaneously that are conflicting, it will be, whoever comes in last will get, they can check to make sure that their changes still make sense.
So you were saying earlier that the OVSD vSwitch D runtime information is also replicated back, is it propagated over to OVSDB?
So the question was about whether, my statement earlier about runtime configuration going to OVSDB server, and so some of it,
Configuration state.
state. And so there is some state, but it's not, so for example, flow table information that comes over here, that's not sent over. It's just things like the open flow port numbers that are dynamically assigned. Statistics get sent over to OBSDB server, interface.
Statistics, so your counters and things like that.
Yeah, exactly.
Runs in real time or as close to real time as real time you get?
Well, no, I mean, it's the way that we do it, you can be, but then it killed performance. So what what we do by default is every 5 seconds we update it. But I mean, it's configured, or it's, it's just code, but I mean, that's what we decided to do.
One question.
Yeah.
So the OBSDB uses the bidirectional JSON to talk to the controller. So if you look at the RFC, I had a specific question on why didn't we use the, so for example, JSON as a set mechanism, right? You can do the dictionary based where I can set the values. Key value pair you can set in JSON, but the OBSDB prefer to use a bidirectional array instead of a dictionary kind of a mechanism. Right?
Okay, yeah, that'd be a good question for Ben, because Ben designed the protocol. So I reviewed it, but I didn't. I wasn't that familiar with it to ask those sorts of questions. So Ben would be a good person.
Sure.
Yeah.
OVS VS couples it over the OVSDB server. So whatever configuration you do, that kind of works in OVSDB server. And the OVS OF couple, that sits over the OVS vSwitch table.
Correct. That uses an open flow connection. OBS OF kettle sends open flow connections to OBS vSwitch D. OBS VS kettle sends OBS DB connections to OBS VS kettle. And then OBS DP kettle, from interfacing with the data path, sends netlink messages down to the kernel. Any questions? Yeah.
You said that OBS vSwitch D doesn't have anything persistent in it, right?
Right.
So, and it can connect directly to the controller.
Right.
Is there any way to just use OBS vSwitch D connected to a controller without the OBS D?
So the question was, is there a way to have OBS vSwitch D connect directly to the controller without using OBS DB server? And no, not really, because it has configuration of like the controller IP is stored in OBS DB server. Things like the bridges that are created and the ports that are attached to the bridges, that's all configured in OBS DB server. So, and then at the bottom you can see there are these, I mentioned the tools that describe how you can interact with OBS DB server. So as I mentioned, VS Kettle is used to do configuration like adding a bridge or something. That's sort of a high-level description of, or high-level commands that you can run, like add bridge, add port, so it knows how to do those things. Like, so we wrote code that says, oh, if I add an interface, then I need to create the records for that interface and then find the bridge interface and connect them. You could do that at a low level with something like OBS DB client, but OBS VS Kettle is just a much nicer interface. And so there are these sort of OBS DB tool is what you use to do things like configure the database or compact the database. The OBS DB client interfaces with it at a low level where you're actually doing like the JSON RPC calls. And then OBS App Kettle is a utility that is available to communicate with any daemons, and it connects, and then it can get it connects to a particular daemon, and then it has command. It can figure out what you can have commands that are specific to that daemon. So, for example, you'll see us sometimes say, run OBS App Kettle, and for the database, you could do things like change the login level, compact the database. If you connect to vSwitch D, you could dump the hidden flow tables or trace packets. And so there's this OBS App Kettle command sort of varies, but it's a generic way of talking to daemons in Open vSwitch. So there are a lot of tables, or quite a few tables in that we use, but these are sort of the most important one. So you have the Open vSwitch table, which is the root. So there's just one entry in that, and then it points to, it has a set of bridges, or sorry, it points to the bridge table, which then has a set of bridges that define, if you have a BR0 and a BR1, those would all be rows in the bridge table. And then if you had ETH0 attached to BR0, then it would have a reference to the port table. And then ETH0 would then have a reference to ETH0 in the interface table. And we have this difference between ports and interfaces to do things like bonds. So a bond would be if you had a bond 0 device that was made up of ETH0 and ETH1, you would have the bridge would point to a record in the port table that has bond 0, and then it would have the port, that port row would have references to the interface table to ETH0 and ETH1 that were in the interface table. We mentioned the OpenFlow controller is configured in OBSDB, so there's a controller table, and so the bridge would contain pointers to the controller table. So if you had BR0 that was configured to some particular controller, that would happen here. And similarly, there's a manager table, which is which is what OBSDB server uses to connect to the manager that speaks OBSDB. And so these are very similar. This is to connect to OBSDB, and this is OpenFlow. And then there's a pointer to the SSL. Right now we only support one set of SSL credentials, so the manager and the controller have to use the same SSL credentials. That actually would be something that would be worth looking at changing, but we don't support that right now.
And is the interface table populated by scanning the interfaces?
Yes. So the question was, is the interface table populated by scanning? And no, the interface table is it's only populated, it's not automatically populated. When you run something like OBS OFKettle, vSkettle add port, it will create the interface and the port and then link it to the bridge.
And then also validate to make sure that interface exists.
No, it doesn't. And so that's actually one of the things that that Ben had listed as something that would be better or that would be a good improvement, is that we have that problem where if you say, add ETH5 and there is no ETH5, these will all the records will get created, and then you'll just you don't get any notification from vSkettle that it failed. And so that's one of the suggested changes. And so Andy is looking at adding support for that during the hackathon.
The controller has many bridge ID. The controller table can have many bridge ID like a DP ID.
So was the question that
the controller table maybe have multiple bridge ID.
So can you have multiple bridges connected to the same controller? Yeah, so what you would have are multiple controller entries, and then each bridge row would then point to those different controllers. Even if it's the same IP address, you would have different controller records.
Okay, it's just this table is just in the local OS Open vSwitch, right?
Sorry?
It's just inside of the Open vSwitch, the local. The table.
Oh, is the table? Yeah, this table is on every OBSDB server instance. So this table exists.
Not the controller table.
Right. Oh yeah, the controller's configuration. Yeah, that would be completely different. That's outside the scope of how they would extend this. Other questions? So debugging the database. We discussed OBS vSkettle configures vSwitchD, but it's really just a high-level interface for OBSDB, the OBSDB protocol. So there are things like add bridge, list bridge, you can add port, list ports, all the things that you sort of expect. This command is actually fairly useful. This OBS vSkettle list and then a table. So you could do OBS vSkettle list bridge, and then it would dump all of the bridge tables. And so then you would see all of the configuration, like the controller records and the port records and all of that. One of the commands that's not listed here that's also useful is OBS vSkettle show. It doesn't take an argument, and then it just shows sort of the most interesting things about the configuration. So it would show BR0 with attached interfaces and that. And then like the controllers that are configured. It leaves out a lot of information, but it's sort of a snapshot the basic configuration of the switch. There's this OBSDB tool command, and that's this show log command is probably the most interesting one in OBSDB tool, and that's the one that shows you what the log looks like so that you can see all of the changes that happen. And then you can add M flags. The more you add, then the more detail. But you'll want to run at least one -M to see the changes that are actually being made. Oh, here's an example of the show log output. So, you would start off with some known state, and then you can see that there are these records that indicate the changes. So that they're just, the record number just increments. You can see when the change was made, and then this is, I mentioned that there is a comment here. And so this is when you run obs-vs-kettle, this is adding a port, and so this is what Zen uses to modify it. So they add all of these, there's a bunch of changes. When they want to do something simple like add a port, they do a bunch of other things as well. And so this is all describing how vs-kettle was called. And then down here are the actions that were required to make this happen. All right, so now we'll go into the forwarding. So the way that the Linux bridge works, all packets, you have this Linux kernel module, and all packets just go through that kernel module. So if an unknown address, someone communicates for the first time, it will update its local MAC table. If it doesn't know where to send the packet, it floods it, does learning automatically. But everything stays in the kernel module, and it's fast. Everything stays in there, but it's very simple. It just does L2 learning. OBS vSwitch is designed different. The kernel module is just a very simple cache. The complexity is all in this vSwitch process that figures out what to do with it. So the first time a packet comes in, it gets looked up into the hash tables in the kernel. If it doesn't find an entry, it sends it up to vSwitch, and so that's what this purple path is. So the packets will go up to vSwitch. It will figure out what to do with the packet, and then it will install a flow in the kernel module about what to do with it next time a packet comes in that looks like that, and then it forwards it on. So the next time packet, because it has a kernel entry, now it stays in the kernel. So there was we had some performance issues before because this kernel module prior to 1.11, the kernel module just had a single hash table. We pulled all of the header fields off, and then we had an exact match entry. And that worked pretty well for most traffic. If everything is working, kind of how you would like to see your traffic working. But if someone did something like a port scan, each time, even if you didn't care what the port was based on your configuration, the packet would miss and get sent up to OBS vSwitch to figure out what to do with it. And so the performance is really bad on something like a port scan or something where you're changing lots of addresses. So even if you had vSwitch configured as a simple learning switch, and all you cared about were the MAC addresses, if you did a port scan, all of those new packets would end up going back up to the vSwitch process. With the introduction of megaflows, we actually look at the configuration of vSwitch and then see how much we can wildcard, and we push down wildcard entries now down into the kernel module. So if you match the TCP port, you'll still end up with that situation, but if you don't match on it, then everything stays in the kernel module. Yeah?
How many flows can we have on the kernel module?
So the question is, how many flows can we have in the kernel module? And the hash tables can support hundreds of thousands of entries. We try to keep them lower than that, just because it ends up being a maintenance burden, because vSwitch has to keep track of all of those flows and get stats and everything like that. So we try to actively limit those. But the number that's supported here is fairly large. And then in later versions of vSwitch, or more recent versions of vSwitch, we've gotten we've made vSwitch multi-threaded, and we have threads now that are dedicated to getting those stats, so we're increasing the number. So before, we would try to limit the number of kernel entries to like 5,000, even though, it could support, hundreds of thousands. The maintenance, then vSwitch would just spend all of its time trying to get stats and update things. So we now have dedicated threads that can get those stats, and so we can scale it much higher. Yeah.
On this, the open research, right? You talked about megaflows. If I consider my switch to be pure learning, right, possibly like that, then what was the reasoning behind handing it up to the OVS switch vSwitch? I mean, I would have thought that was based on the mode, how it's configured. I'm just trying to find out the reason behind why the earlier versions, before you had megaflows, why would the packets go all the way up?
Okay, yeah, so the question is, why did we ever have an exact match cache? Because it seemed like a poor design choice.
Yeah.
So the reason is that we, well, one, it was fairly complicated to add that because you have to figure out dynamically based on the configuration. That's one part. There was, at the time, there actually were there were some nice things about the way that we did that, where we had exact match entries. So, for example, something like bonds were fairly easy to implement because everything was an exact match entry. So we didn't have to introduce the concept of a bond in the kernel module, because what we would do is, you would hopefully you're not having a whole lot of people that are communicating, but you could look down at a very precise level and push down flows that then bond traffic across multiple. That if you want to share an interface, you can break them down at a fairly fine level of detail. And so you can, I mean, it was one of these things like I don't think that we realized how much of a problem it was until we started deploying it. So, I mean, it was, there was I think some sound technical reasons for why we thought the approach was a good idea, but then in practice it didn't end up working very well. And then, for scale, if you had a few people who were doing port scans, then it would bring vSwitch down. So it's just one of these things that it seemed like a good idea at the time, but it was.
Can you explain again about megaflows, how it's implemented just
So what happens is when so the question is, how do megaflows work? And let me just look real quickly. I haven't looked at these slides for a few months, so I'm trying to think if I have some slides on megaflows. Let's see, I have one, but okay. Well, we'll look at the slide. There's not a whole lot of information. So what happens is that with megaflows, when a packet gets sent up to vSwitch, we start off with a state of certain fields that can't be wildcarded. So what we do is we look and say the ingress port can't be wildcarded, and so we came up with a new word, unwildcard. So we unwildcard the import field. But everything else is wildcarded. And so then as we look at the flow table and someone looks at a particular field, then we unwildcard that. For example, if you look at the IP address, then we would look at we have to look at the ether type, and so then that becomes unwildcarded. And then we would look at the IP address, and then that becomes wildcarded. And so, and if you did TCP, then you look at the, as you look at it, any field that we look at in determining what the field is, that becomes unwildcarded. So there are certain fields that automatically end up always being unwildcarded because of the design. So things like we ended up looking at the source MAC, dest MAC, and ether type. We had various I'd have to, I can get into it if we want, but we basically have to look at those for doing some of the things that we do for OBS. So those always become unwildcarded in the ingress port. I think those are it. So basically the L2 address, or L2 stuff, and the ingress port, those always become unwildcarded. But then everything else is pretty much fair game. So if you have flow tables that look at any field, that becomes unwildcarded, and then the prerequisites for getting to that point in that entry, or that thing that you were looking at. Then there's also configuration things that can also affect it. So for example, if you enable bonds, the bonds because of how I described things with the exact match, that ends up unwild. You basically end up with an exact match for bonds. Now, Andy, who's left now, but he just yesterday got some code committed to move away from that model, where we're adding actual recirculation to the kernel so that we can do bonds in the kernel module, so that so that we don't have to unwildcard all of the ports for bonding. But they're just various things that basically, if because of the configuration, we have to look at a field and we unwildcard it. And that's how Megaflows works, is that you start off with a state, you just assume everything can be wildcarded, and then you start taking away wildcards as you need them for your configuration. Make sense? Yeah.
If you have a pre-existing flow, you're already going through, and now you unwildcard it, suddenly you have a whole bunch of packets hitting you.
Well, so what would happen is, that shouldn't happen. So if the configuration is consistent on vSwitch-D, so we look at the way that the classifier is implemented in vSwitch-D that keeps all of flow table entries. In the way that we do the lookups, we'll never end up with a case where we have to change the existing entries unless there's some sort of configuration change.
On a configuration change, that can cause that problem.
Oh, okay, yeah. So if someone came through and then added a new flow, then we would revalidate all of the kernel flows and then boot them all. Not all of them. I mean, all of the ones that were affected by that.
Would that not cause all those packets to suddenly show up in the user space now?
It would.
In the middle of the flow?
Yeah. Yeah. So.
Yeah.
Oh, sorry. The question: was that a problem? I mean, there's not a lot we can do. I mean, you could try to recorrect everything, but I think in general, we don't see a lot of people who are a lot of changes that are happening to the flow table. You sort of connect to the controller, and then the controller does state. Every once in a while, something changes and it does it. But I mean, it's not something that we see happening constantly.
So you mentioned about the megaflows that specifically like ports and everything, you unwildcard it and the rest of them are combined together?
Sorry?
So in the megaflows you mentioned that you unwildcard some specific ports or some other fields?
Yes.
And the rest are combined together? I mean, how exactly the megaflows work? I didn't get that.
So,
I mean, there are normal flows, so which will have a specific field with wildcarding.
So the kernel module is always, one of the things that we did in the Megaflow design was that we said there could be no overlapping flows. So everything, we have I don't know how much we want to get into the details, but we basically have a set of a set of hash tables that we look up in the kernel module. And so they're guaranteed to be non-overlapping, so that the first entry that we find that matches, we can use that. vSwitch-D is responsible for figuring out how to generate those. And those are generated, how much wildcarding can happen depends on how vSwitch-D is configured. So if you match on the TCP port, then the TCP port will be unwildcarded for any entry that's coming through that could match on that information.
So I still don't get how it relates to Megaflow. What exactly?
So Megaflow is basically is a term that we use for wildcard entries in the kernel.
Oh, okay.
So there used to be exact match entries. So everything, all of the fields, like 17, I think there's at least 17 fields, including the IP TTL. All of those fields had to match exactly, and if they changed, then it was a new entry in the flow table. But if you don't look at the TTL, as you usually don't, with Megaflows now, that field would be wildcarded, and so if the TTL is changing, then it wouldn't require a separate entry.
Okay.
Does that make sense?
So based on the wildcard entries, these entries will be based on appropriate hash tables. So
yeah.
When the hashing comes, you choose which hash to.
Yeah. So what happens is that the way that it works is that there are multiple. So it's called a tuple space search, and so we have a set of hash tables. So it says, for example, if you have some entries that look at I'm going to simplify things so I don't have to list all of them, but let's just say you had something that was looking at the L2 address, L2 source, and then you had one that looked at the L2 dest and L2 source, you'd have two hash table entries.
Right.
And so if you had, if the L2 dest, or which one I said was, okay, the max on the specific source and both is one of them also. They can be non-overlapping. They can't be overlapping. Source. Max on the source. Couldn't appear in both tables. Because that would be. So what you would do is, if the source ever looks at the destination, the L2 dest, then it would always be exploded out as an L2 source and dest. So there are two hash tables. But then if that L2 source never looked at L2 dest, then it would just be in that L2 source. So there's, depending on, you'll have a hash table for each combination of things that are unwildcarded.
Right.
And so, and then those are guaranteed to be non-overlapping. So right now, we haven't optimized that so that basically when a packet comes in, when the order in which vSwitch pushes down those hash tables is the order that they'll be consulted. That's an area of optimization that we should look at, which is reordering the order in which they're matched or they're looked at. But that's not something that we do right now. But so if you run the obs dpkettle show command, you'll see the number of, I think we call it masks, and the masks indicate how many of those hash tables there are. So you imagine, on average, hopefully, you're probably, as you increase the number of hash tables, then you're potentially, or the number of mask combinations, then you're possibly consulting, you're going to be consulting more tables on average. Right. And so we're looking at various optimizations for that, but right now that's not optimized.
Yeah, sure.
Okay.
So for two flows having a specific entry and a non-specific entry, for example, whatever something field or the tuple you called about, one having TTL unmasked, masked, and another having a specific TTL. So in your case, you will have for each hash table, you will have specific source mask, whatever. Yeah. And finally, every entry will be common for both the flow entries, and the final entry, the TTL will be, one will have whatever, 255, or something like that.
So if you had the, if you took the TTL example, I think the way that you were describing, you would actually match multiple tables, but that's not the way the design works. The design works by, you would have if you had something that was matching on the TTL, you would match on you'd have to match on the IP protocol field, and then you would match on TTL. So that would be one entry, and then hopefully you'd have some sort of thing so that you don't have to, worst case, everything then devolves down to having to look at the TTL. Hopefully you can narrow that down to, there was only a particular IP address cared about the TTL, and so then you would have, a match, then that table would match on the IP address, the IP address wouldn't have matched something else, so that it would be forced into that field, so you'd only have an explosion for that particular IP address. So that's kind of a poor explanation, but does that make sense?
Excuse me, I had a question.
Can I say something like that? If the 17 fields form a flow, then if I select, say, 5 fields to form a tuple, that could be called a mega flow?
Yes. Okay. Yeah.
So I can select any field specifically and then determine that rest are like unwildcarded and wildcarded flow. This forms a mega flow.
Right. Yeah, that's how it works. Is that if you don't look at a field, it's wildcarded, and so then the hash table will be consist of the things that are unwildcarded.
So who gets the priority, the mega flows or the normal?
So there are only mega flows in here, so that so there are no, I don't know what a regular flow you're talking about, like an exact match flow. Yeah. So we're hoping that you don't have exact match flows, but if you had exact match flows, then that would just be a mega flow that just had all of the fields unwildcarded. So that would just be a very big hash table. We've talked about doing something, like I said, we need to optimize how the lookup happens in the kernel. One thing that we've talked about is actually having an exact match table that sits in front, so that the so you end up sort of with multiple levels of caching, basically. So you'd have your mega flow in here, and then then we would do a hash. We would first look to see if we have this exact match table. But before, where we had that exact match table where we were sending it up to vSwitch the penalty would be much smaller, and so that you'd have this exact match cache that's just sitting right in front of the mega flow, and then consult that table. So, and then that way that doesn't matter how many, or relatively speaking, it doesn't matter how many different mega flows you have, or sets of tables you have, because you have a fast cache in front.
So if I'm not mistaken, the mega flows was in 1.9 or 2.0, right?
It was in 1.11.
Okay. Yeah, 1.11. So before that, there were exact match flows with the
Yes. Yeah, so there was only one table, and it was all 17 fields, or however many we could match on.
And those same tables were in vSwitch as well?
So vSwitch would figure out how to populate those tables in here. vSwitch you program it the same way, where you have open flow and other configuration effects with the.
But it doesn't keep a copy of it.
Well, yeah, it had a copy of it, but it sort of was an implementation detail. It wasn't out of requirement. It was just
okay.
But yeah, there was something called facets and sub-facets, and those kept track of what was actually happening in the kernel. But we got rid of those in 2.1. I think the facets and sub-facets went away.
Sorry again. So depends on number of hash tables that we have.
Yeah.
The performance is going to dip, right?
Correct.
So we cannot say that the performance a priori unless we know the kind of configuration that comes from the controller or OCTO.
Right. So that's why I was saying that we're looking at how to optimize it. But yeah, so the performance right now, though, we haven't seen in practice that that we have. Typically, you don't have that many tables, hash tables that you have to consult. Yarno, who's sitting near you, has added a bunch of optimizations now that are going to blow that out. And so we have like trees that now or tries that will optimize things like TCP ports and IP addresses, and so then you're going to end up with more of these combinations. And so it's before in practice we maybe saw, I'm going to guess, but less than a dozen hash table entries. But now there's going to be potentially a lot more.
See, personally, I'm working on OpenStack kind of integration with OpenDaylight, right? So originally we started with the pure L2 mechanism. It's so simple with MAC and port and tunnel, we can able to do that, right? Now we're looking at security policy groups.
Yes.
I immediately see there's a possibility of exploding this into multiple groups. So, so again, the original question back about number of entries that we're talking about on the hash tables, right? Now, originally we had this problem of one dynamic table, and number of flows because of the management, right? So one table has this problem of number of flows, but performance is perfect.
Okay.
But with more number of hash tables, we can expand the number of flows, but performance is going to start dipping now.
Right. Yeah, I think that the performance, right now, when you start looking at because if you want to implement security policies and you're looking at the L4 ports, you're basically going to end up with almost the same as exact match entries. So actually the problem is, it's worse than that. It's worse than the fact that you'd have lots of tables. It actually is that because you're matching on the ports, those ports will all have to go to vSwitch.
Right.
And so that's actually something that Yarno is working on, which is that right now, we say, did you look at the L4 port? And then that L4 port becomes, as an entity, all 16 bits end up being, it's a yay or nay on the unwild carding. And now we're looking at, actually bitwise, looking at, for example, you could probably, most of your security policies aren't going to have the first bit or two set. And so you can unwildcard those individual bits. But now you're starting to, we do that dynamically, and then you do end up with an explosion of flow table entries. But the goal is really, we'd much rather have multiple hash tables in here, because that's going to be much more efficient than going up to vSwitch. That's very expensive. It's not only because it's of locality, because you have to go farther, but the vSwitch tables tend to be very complicated. And so then you have to go and consult all of these tables and figure out the configuration. And so consulting a couple of hash tables is pretty cheap in comparison to having to go up and then figure out all of the configuration again.
So if the field that you're looking further down have any kind of dependency, they have to choice for connecting.
Yes, the security.
UDP port, then you have to check, make sure the protocol has an IP.
Of course,
you're
yeah,
going to go backwards.
Security policy is just one example that I came, right? I mean, there are a lot of effort for SS services coming along. Yeah, they're going to keep.
So one of the things that the breakout items that I had suggested talking about is for L4 through L7 services, and what I'm looking at actually, I mean, just for the security profiles, is actually using something like the Linux contractor, so that you send packets to the contractor, and then, I mean, you're still going to have some policies, but I mean, I think you're going to end up with better, you're going to end up with a better policy, you're going to end up with better enforcement than you can currently do with OVS. So if you're interested, I recommend talking. We can get into the details about that, about what I was thinking about that. Thank you. Okay, so, all right, we covered a lot of this, but so the OVS vSwitch is sort of that main thing that figures out what to do with the packet. It uses OpenFlow to connect up to the controller, OVSDB to the OVSDB server, speaks netlink to the kernel module, and then it also can talk to the system through that netdev interface that we talked about as well. You can do multiple bridges. This packet classifier is what we talked about with the thing that looks up the OpenFlow rules and then figures out how to generate megaflows, which are and then it does things like mirroring, bonding, VLANs. They're all handled by vSwitch. And then another important thing that catches a lot of people by surprise is that the kernel module is really pretty dumb, and that it has a cache, and that's really it. OVS vSwitch is completely responsible for managing it. So if you kill vSwitch while there are flows set up in the kernel will keep passing them out. They'll never time out. So it's completely managed by vSwitch about how long packets stay in the kernel, when they should be ejected, and all of that. So the kernel module, it's the fast forwarding plane. It also handles tunneling, but those are really the end of its requirements. So it mentions that the flows the mega flows that are in there have to be non-overlapping, just for efficiency purposes. So the first time you find an entry, you can run with it. Okay, I think I've discussed all of that, which is just that it's fast and simple. Yeah.
If you don't mind, could you, this is an area of confusion for me, especially the accounting part.
Yeah.
So when you're trying to count, FTP or VXM,
yeah.
When you're sending the packet out, the rule itself will tell you what to prepare the packet, so there's an encapsulation error and all this stuff.
Okay.
So it doesn't hit a daemon, right? I mean, it's just done by, I like to understand the data path for that, and also when the packet is received with the encap header,
yeah.
it has to hit a daemon. But when you're going down, I'm trying to follow that, who handles the encap and decap? Is it done within vSwitch?
Okay. So the question was about how encap and decap is handled by the kernel module, and so that's all handled by the kernel module. So there is no on receive and on transmit. That's not handled by a daemon that's in user space or anything. Okay. So so some of this has changed. So we used to have our own tunneling implementations that were in the kernel module that shipped with OVS. We've been working on abstracting the tunnel interfaces in the kernel so that we use those. So before, like, there was a GRE implementation in the kernel, and we had our own GRE, and same with VXLAN. And so what we're doing is we worked with the Linux kernel community, and then got to a point where there's sort of a common code that implements those things, and then there's the standard Linux GRE way to interface with it, and then you can OVS uses it as well. So it's sort of a when you do something like append like you want to say put it in this VXLAN tunnel, then we prepare the information, like the header information, and then I think the packet I'm a little fuzzy actually on how this works now, but the packet gets generated and then it gets sent to the Linux IP stack, which then forwards it out. And then the same thing on receive, the packets, is sent to the IP address of the hypervisor of the host, and then it passes through the IP stack, and then we have hooks that, that like we receive the packet, basically. I'm not sure if that answers your question, but.
Yeah, I mean, the reason I was getting confused was when we were looking at a certain issue, translating receive the off. Because there would always be packets, but some packets show up on the bridge interface, IP address configured with it, but then translate show no packet on the bridge interface with IP. So that led to at least a conclusion on our part that translate is not hitting the IP stack. Because the counter for the IP interface, for the bridge interface is not going.
I think, yeah, but I think that what will happen is that the when the transmit happens, yeah, it probably wouldn't hit, like if we have like, I think in your case you're talking about like you have an integration bridge or something like that.
And then integration bridge, and there is a VRE.
Yeah, then there's that we call the PIF bridge.
Yeah.
And so I would think that the PIF bridge though probably had its counters go up, right?
Not on the transmit.
It didn't.
But only the receive would show. Oh, we can take it out.
Okay, yeah, that would surprise me just because it does end up, if it's being transmitted, it does go through the IP stack, and I would expect, and it goes, if you have that configured, that PIF bridge configured as OVS, then the OVS handles it. So I'd be surprised. Okay, but yeah, we can look at it. Questions?
You asked a question that I think is related.
Right. Yeah.
I was wondering why.
Sorry, one second. Could you repeat the question?
Yeah, I didn't ask you. I was wondering about the recirculation that patch that's out there now. My project is 802.1ab and 8.8, and I noticed the recirculation seems to be necessary for MPLS, so I suspect it's necessary as well for AH and AD because they are left of VLAN. But I haven't convinced myself yet that it is necessary. I was wondering if you care to comment. Thank you.
Okay, sorry, Sue. You were sort of cutting in and out. So you were saying that you were curious if it was necessary for AD and AH?
That's correct. 802.1ab and 802.1ah.
Can you remind me? I don't remember what off the top of my head.
Well, sometimes they're called PB or PBB, provider bridge or provider bridge backbone, and they basically are nested VLAN. Q and Q or back to back.
Oh, okay. Oh, Q and Q. Okay. Yeah. So.
Q and Q and 1A is Mac and Mac.
Oh, okay. Okay. Right. Yeah. So I think that there has been, I think that I know for Q and Q, that's something that we've definitely talked about because that's something that we get requests for quite a bit, and so I think that would probably be a reasonable way to do it, but I can't remember what the current state is of that. And then in terms of Mac and Mac, I don't think that's that's something that's part of the OpenFlow spec. I think that's something that we would be interested, that could definitely be added. I don't know of any, I don't know of something that my group would be working on to add that. So, but I mean, I think that, you could probably, trying to think if you actually need the recirc action for those. I'm not sure that you do, but I'd have to think about it.
You know why I asked why Simon feels he needs to recirc for MPLS?
Why does Simon need to for MPLS?
Yeah, because you need it for MPLS, you may need it for 802.1 AD as well.
Okay, yeah. So the question is why do we need it for MPLS but not for like Q and Q? And the problem with MPLS is that it doesn't have an ether type, so it makes it hard for us. So you need to sort of classify the packet. Like we can't do it in one shot because we have to pull all the headers off at one time when we're looking in the hash table, and you can't do that with MPLS because there's no ether type. Because depending on what the tag is, then you interpret the packets, the bytes after it differently. And so But MPLS doesn't carry, its header doesn't have an ether type in it. Yeah, so we don't know how to interpret the bytes that follow it. Yeah. So Q&Q, there is an ether type, so we could process everything in one shot. You know, when we're pulling the.
Also, there is a bit which says this is tax bit.
Right. Yeah.
Multiple MPLS tags, there's a bit you can look at, similar to that, you know.
Yeah, there's like the bottom of stack. Yeah, right. That, yeah. And so, but the problem is that when we're in that stage where we're looking up the packet and we want to pull all the headers off, interpret them, and then throw it against a hash table. And so with Q&Q, you can, because, you know, you say, you know, it's like, okay, well, this has another, VLAN header in it, and so then you can then interpret those, and then it says, oh, okay, and then in here is an IP. You can do that in one shot. With MPLS, the tag itself describes, you have to be able to interpret the tag, so you can't do it in one shot. You have to have one pass where then you say, okay, yeah, this should now be treated as IP, so then you recirculate it back, and then, you know, or it's another MPLS tag, so you have to do another recirc. So that's the reason that we have to use recirc for MPLS. I don't think that we would need it for Mac and Mac and for Q&Q.
Yeah, you know, well, then you're probably right, because there is a ether tag embedded in the CPID or whatever for each layer of encapsulation, I believe. So I figured that, you know, from the user standpoint, from the controller standpoint, they could do each layer strictly in a different paper. So we do linear them.
Yeah, sorry, you're sort of going in and out. I can't. This might be a better discussion to have on the mailing list, or we could talk offline. Just because I don't know if it interests everyone, and it's a little hard to hear you. Sorry. All right. Any other questions? The UES side?
Previous slide?
Oh, previous slide, yeah.
So actually, about the tunneling, the flows in the tunneling stuff.
Yeah.
So when we start VXLAN tunnel or any other tunnel, I saw that you could match flows only when you have a port which have a tunnel. You can't match the keys on any other flow which are passing through the switch but don't have a port. So is that intentional?
Sorry, I didn't understand.
So if you have a flow which has a VXLAN,
like the VNI, if I'm not? Like
it has a VNI in it, and it's just going through, so that you're forwarding it to some other.
Okay.
But you can't match it to it unless there is a port which is doing VXLAN processing on that bridge. Is that intentional?
Well, yeah, I think that we don't.
And basically what I'm trying to say is that the 15, 16 fields which you consider, the VNI is not one of the fields. Is there a way to put that in there? Because
I think that there's a special case for tunnels that we always exact match the tunnels, and so I would think that the VNI is included in that tunnel header that we match.
So what I'm trying to say is that if there is a terminating VXLAN port or initiating VXLAN port, only then the processing for the tunnel happens. Supposedly you have a switch through which the flow is going through and has a tunnel, and you would process it on that, but it doesn't have any port for tunnel, or it's not the end point, then it actually doesn't process it. You simply have no way to process that flow.
Yeah, I mean, I think because we wouldn't, that ends up being sort of deeper inspection, because then you would have to, if you're transiting it, then you're going to say, okay, this is, for this particular port is VXLAN, and then you're going to interpret the bytes differently that follow the UDP, right?
I mean, you could do it for VLAN, but you couldn't do it for VXLAN. So I was just confused why. Right,
but like VLAN is its own ether type. VXLAN is a UDP packet, so you'd have to then interpret the bytes differently. And so right now, we terminate this. Sorry.
The only thing I want to know is anyone working to add that support, or is it?
No, this is the first I've heard of someone wanting to do that. You're basically talking about if it's transiting the switch, if you're matching on the VNI.
Exactly.
Yeah, I haven't heard of any discussion about that. I mean, Yeah, I mean, it could be a little tricky, and then it could also, could affect performance, because then you're having to look at the UDP port and then making it, and then and then looking at the packet. But yeah, I haven't. It's an interesting point. I hadn't thought about it before. But yeah, I'm not aware of anybody who's working on that.
Hello, Srinivas here. I have one related question on the same topic. Can I continue?
Yep. Yes.
Okay. The question is with respect to the tunnel ports. Now that we have flow-based tunneling, so if I create two switches, S1 and S2, can I have wildcarded? I mean, the regular tunnel ports on both of them. I mean, we couldn't get it working, so we're trying to understand how does it actually work. So if I have only one switch with a plain tunnel port, every parameter of that is wildcarded and flow drives the thing. The outbound path, I don't have a problem, but the receive path, I think the packet, the assumption is like the packet would go to both the switches, and the flows would select it whether to allow it into the switch. So I mean, sort of confused on how it actually works.
Yeah, I actually don't have much experience with flow-based tunnels, so I don't. Yeah, yeah. That if you don't mind posting that on the mailing list, or we could talk about it offline. I don't remember the details of receive side for flow-based tunnels.
Sure. Yeah.
On the reset, you see the reset and how it's implemented, right? So now we have the open flow. One of the you have the go-to table support.
Yeah.
It can do it cannot do reset, but it can go front. You cannot go back, right?
Right.
But reset can do the going back tables and whatnot.
Right.
So say I want to use open flow to control the OVS.
Right.
And I want to do a reset.
Yes.
Today I cannot do that. Right. Unless you use the NX emitters.
I thought that we support GoTo.
So if I use GoTo and this is open flow, right?
Yep.
Can I point to the table?
Yeah. So the recirc that I was talking about in the kernel, that's different from the recirc at the open flow level. So at the open flow level, we don't actually need the recirc. So what happens is when the packet comes up, we figure out what to do with the packet. So if you have go-to tables or resubmit or however you want to, consult the open flow table multiple times. We follow the path of the packet, and that was one of the reasons that I was talking about why it's so expensive to go up to user space. So if you have this very complicated flow table that is doing, we'll see, a dozen resubmits easily. Then you have to look at all of those tables and figure out what to do with the packets, and that could be go-to or whatever. But then we figure out like an efficient way of implementing that as an exact match that gets pushed down into the kernel, or a mega flow that gets implemented into the kernel. So we sort of unravel, we figure out what path that took, figured out what the actions were, and then we push a cache entry that describes it. So the research that happens at the open flow level doesn't impact down at the kernel. What we're talking about, the kernel level research had to do with things that were hard to implement, like MPLS or bonding, where we have to push down we either have to implement bonding, or we would in the kernel modules we didn't want to do, or you would end up with these exact match entries. But they're completely disjoint. I mean, they unfortunately use similar terminology, but they're not related. Okay, I mean, I think. All right, so the user space, this is the OVS vSwitch D. We've gone over really all of this, but the packets get sent up to vSwitch D. It looks at the classifier, which is what contains all the open flow rules, and then it accumulates the actions that apply to that. If you have something, depending on your action, so if you have a normal action, then it will do things like L2 learning or implement bombs. And then, then if you have things like mirroring configured, then it adds those rules as well to the kernel to the mega flow entry. And so, As mentioned, prior to 1.11, that was always an exact match flow. And then starting in 1.11, we generate mega flows. So this is also a review. So when a packet comes in, we pull the headers off of that packet. Then we hash. We use that as we hash the header field, and we use that as an index into the hash tables to do the lookup. And then if we find the entry, then we update the counters and then apply the actions. And if it's not found, then we send it to vSwitch D, which then does all of the processing. So that's handled by vSwitch D. So the kernel never expires entries and never removes entries on its own. vSwitch D will monitor them, see if they go idle, it will eject them, or if the flow table configuration changes such that it needs to update them, then it'll remove them. But it doesn't push down entries like proactively. It only based on like misses will it, populate.
For the normal action, are there any specific flows generated by vSwitch D which are pushed to the kernel, or every time for normal action the packet has to go all the way up to vSwitch D and back?
Well, so the normal action would be, we'll apply L2, L2 learning and MAC address. So, if it doesn't know where to send the packet, then it would push down an entry that floods it, like sends all of the ports that are in that bridge. And then once, then if the other side responds, it learns what the MAC address is, then vSwitch D then will figure out, now we don't have to flood that packet, we know what the port is, and then it will update the kernel entry, and then only forward it to the particular interface. But there's no concept of normal down in the kernel, it's all up in user space. But user space or vSwitch D will update everything, appropriately.
So if the module is on and if you kill vSwitch D, the normal action should stop working.
Well, if you kill vSwitch D, then but if the addresses were learned, so if you have configured as normal, and then it knows that these two MAC addresses are communicating, those guys are staying active. If you killed vSwitch D, they would continue to be able to communicate with each other. Now, if they moved, if you moved the one side to a different port, normally learning would happen and it would get updated, but that won't happen. It'll just continue sending packets to the old port.
What I'm trying to say is that if you don't have vSwitch D, then the flooding wouldn't occur, so that the normal ARP recognition and stuff wouldn't go through.
Right. I mean, basically the configuration in the kernel will just stay frozen until vSwitch D starts again. So whatever the state was when it got killed, it will stay that way. What was that? Sorry, I can't understand what you're saying.
In order if they could also maybe punch through things on the vSwitch IRC.
Oh, it's probably gonna be hard for me to do. I don't know if someone else could be.
Right.
But we can edit if you want. We have the IRC if you want, we can edit for you.
Oh, okay, all right. If anyone has any questions, you can post them to the IRC channel, and they'll get relayed to me.
So, I have an opposite question that what you asked, right?
Okay.
So, say if I want a rule that I don't want to be programmed in the kernel, I want to keep it in the user space. So, are there any specific thing that we can do to be programmed on the?
Yeah, you can't. We don't have any knobs that allow you to control what gets put into the kernel or not. I mean, there are things that the kernel will, or the user space itself is programmed to, not push certain flow entries in. So, it will allow things to continue to miss, but it's all programmatic. It's not, it's baked in.
So, the move instructions is not. What are the instructions that will make the flows to stay on the user space, not on the kernel space? The ARP responder feature that is added new. Yeah. I did a comment that it stay only on the user space and never go to the kernel space, right? So what makes it stay on the user, not on the kernel? Body.
Are you asking why was the design decision made that way?
Well, the decision I understand because of course the ARP responder it's okay to be in the user space. Right? What makes it stay in the user space? What is the special thing that makes it?
Oh, I think it's just that I don't remember how that feature was implemented, but but it's, you just have something basically that there's like, a flag as it's, processing that says, don't push this down into the kernel.
Well, I mean, just to remember, ARP is done along this flow. Right? The request is that. So, does it make sense to pursue that in kernel?
No, I understand that. I mean, I understand the definition not to keep it in kernel.
Okay.
I'm asking what
What is the
it
mechanism? Or how is it?
Yeah.
How is it? So it's because that's an action that is, there's C code around that action. So then there would just be something that, when the packet misses, that it just wouldn't be, you just set a flag that says don't push this down into the kernel.
So yeah, okay, maybe I'll check the flag and use the flag if you want to use it.
Yeah, but you have to use it. But are you going to be modifying vSwitch D?
No, but this is a flow that is currently programmed. Controller can use the NXM. Can use the NXM to program some flows, right?
Right. The flag isn't exposed to through OpenFlow. It's just a flag that's in the user space processing that is figuring out how to generate the megaflow.
Sure.
And then it can just say slow path this packet.
So on the slow path side, say if you have a slow path entry, or there are a lot of slow path entries, right? Are there any limitation or restriction or any performance or scalability issues to keep a lot of flows on the slow path compared to the?
Well, in general, we try not to put things in the slow path. So, for example, we would send there are like CFM or BSC processing. We would slow path those because vSwitch needs to process them, to check the connectivity of the connections. But yeah, I mean, if you slow path a bunch of stuff, then the performance would be bad. So we try to be careful about.
The ARP responder is a good example for keeping in the slow path.
Okay.
Right?
Yeah.
In a typical deployment, open-stack deployment, right? ARP responder is a good feature to have.
Okay.
So, but it explodes number of VMs that is torn, right? It explodes.
Okay.
So it's okay to keep it on the slow path.
Yeah.
So say if you're okay to keep it in slow path.
Yeah.
It's going to impact the performance for ARP. We understand that.
Right.
Which we don't really care. It's okay to have that on. But it has impacts on any other flows. Say I have millions of or like thousands of entries on the.
But it probably, I wouldn't think it would, because I would expect that there would be. I should look to see how it's actually implemented, but the megaflow should be, at the very least, it should only slow path ARP packets, because you would look at the ether type.
Right. So yeah, that's the question. If the ARP respond entries are programmed on the slow path with the notion of keeping it slow, it's okay to keep it slow.
Okay.
So if that's the case, then it will not impact any other flows, should not impact performance of any of the entries, and should scale reasonably better because it's completely on the user space.
Yes.
All right.
Yeah, I think that, it should be specific to ARP packets. And hopefully down even to like MAC addresses, but I didn't look at I don't remember how that's implemented.
ARP responder is implemented the way, I don't take a lot of time here, but it's implemented for ARP entry with looking at an IP address, what are you looking for? Yeah. So it is going deeper level into the ARP packet itself. Okay. So it's much more granular, much more specific around ARP.
Yeah. So that shouldn't cause a lot of packets to miss, because it should be pretty specific.
Yeah. Okay, so we are taking a decision on whether to use ARP responder or not.
Okay.
So if you don't want to cause a lot of performance hit, then we might just use the ARP responder.
Okay, yeah, I wouldn't think it should, but I can take a look at the code and I have a much better understanding. I just don't remember off the top of my head.
All right.
Battery. Oh, yeah. Thanks. Actually, I think I'll just go back there, not trip over it. Thanks. Sorry, was there another question on the phone? Yeah.
The mirroring is done by the user.
The metering?
Yeah. Yes. Let's say I want to mirror a particular flow.
Okay.
The normal path will take minutes. The kernel path will forward the packet. The other copy will go to the user space. That's the way it works.
I actually don't remember. Do you remember, Yarno, did you do metering?
Yes, I worked on it.
Currently, we don't do metering yet. I'm open for metering. And if you can set up meters, they will actually do anything right now. There's some old
I think that's one of the work items that Ben had broken out, actually.
So the contention there is that I have posted an implementation that implements the metering. We don't integrate anything else in there. Like questions like overlapping functionality and getting it upstream or not. So someone familiar with anything resembling metering in Linux kernel today would be helpful in designing out how to integrate that.
So the question was about the status of metering, and so Jarno, who's one of the core developers, had worked on that feature some, and he has an implementation, but the concern was how to get that upstreamed into the kernel. And we, which I think is actually probably a real issue, because like when we actually tried to upstream Open vSwitch originally, there was some friction based on whether you could implement a lot of the functionality of Open vSwitch with the TC module. You know, and eventually it was, you know, everyone agreed, or not everyone, but enough people agreed that it was, the functionality was not overlapping that much. But I suspect that that the Linux kernel community would prefer that meters be implemented with TC somehow. So, but you know, someone would have to take on that project if they wanted to continue it. Yeah.
Yeah, you had mentioned that some work has been done in DPDK. Can you talk a little bit about the kernel interface, how that was done, with the common path or vHost backend?
So yeah, I can try and talk. I'm a little out of my depth there, and the main guy who worked on that isn't here, but I think I can talk at least at a high level of how that worked. So the DPDK port is not, it's primarily aimed at, for like more like appliances, because you know there are issues with sorry, that was actually there are performance. The performance of DPDK is the benefit is keeping all packets in user space, and most of these you know, things like Zen Server and I guess KVM less so, but like there's not an efficient, once you start sending packets to the VM, the performance drops significantly for DPDK. So so we focus mainly on the appliance, which is, you know, sending packets between two interfaces and using OVS to be able to control that. We've been talking with Intel about sorry, I was going to the slide, but about accelerating, and they have some ideas for how to accelerate DPDK with virtual machines, but you know, they have different models. The one that provides the best performance is not safe if you don't trust the VM. So you know, doesn't clean up the traffic, you know, or doesn't clean up the data as it's crossing from the VM into the hypervisor. So I think that's an active area of discussion or of design. But the you know, the DPDK port is a, let's see here, see if I can pull up this, describe how this.
On the WebEx to meet the microphone, I'm getting a little bit of
DPDK port, what we did was we don't have a model. Were you here for this earlier? Oh, okay. So you know, there is no, you know, there obviously is no kernel module for the DPDK, but the original work that Intel did to port DPDK to OVS, what they did was they did this NetDev side to get packets, because that's a requirement to, or not to get packets, but to configure things. But then they ended up implementing a DPIF DPDK port. So they implemented their own data path flow table. And so what we thought would be a better approach would be to use the user space data path. So instead of DPIF Linux here, we have a DPIF NetDev. So we use the user space data path, and then we have a NetDev DPDK that receives packets. So everything stays in user space. And so we, you know, packets get forwarded, you know, through vSwitch, they get handled here in this DPIF NetDev, and everything stays in you know, using the user space data path is what we call DPIF NetDev. and then we focused on improving the performance of that. So we've added, made it so that it was multi-threaded, added RCU so that there's less lock contention for the tables, that sort of stuff. And so the performance that we're seeing right now is over 90% of a 10 gig link on one core being able to forward traffic. So, so the performance is quite good, and I think we still think that we're going to be able to eke out some additional performance from that. Does that answer your question? Or? Okay. Yes.
Question: can you use the vSwitch without the kernel model?
Yes. So you could run a user space. Well, yeah, you could do that. You could run DPIF NetDev, and then you could actually use it with Linux. The performance would be bad. But like the DPDK port, like I mentioned, doesn't use the kernel module, and the BSD ports also don't use the kernel module. They just have a NetDev implementation. They use the user space data path. Okay, so we discussed mega flows. Tunnels. So in tunnels, we implement them as virtual ports. So if you create a tunnel, it's one of the mode that we use most often. So if you create a tunnel, a GRE port, for example, you set the IP address, that pops up as a virtual port. It gets an OpenFlow number. So when you receive packets through the tunnel, it shows up as if it came on an OpenFlow port. If you want to send out you just send traffic to that port number. You can set the key, so like the 32-bit key in GRE or the 24-bit VNI in VXLAN. When you create the interface, you could specify what that is, or you can use match and actions to set those fields dynamically in the flow. And so right now we support GRE, VXLAN, and Lisp, and then you can. The one difference with the Linux kernel is like if you create a GRE or a VXLAN interface, you'll actually, if you do ifconfig, you'll see the interface. But the ones that we create in OVS, you don't see that. And so if you want to look at the ones that are configured, you run OVS DP kettle show to see them. Questions? All right. So, I mean, that's, I guess, should we just keep going? I mean, if people are interested in seeing the utilities, or I don't know.
I will say, I mean, it's, I guess we can see how everyone's feeling. The food actually arrived early, so we actually have all food. If how are people feeling? Want to take a break and have some lunch, or do you guys want to continue on a little more and then do lunch? Anyone?
How much more you have?
I mean, I guess it depends really on, I didn't have a prepared, I mean, this is just, replaying old slides. So, I mean, as much as people are interested, I mean, some of this might be interesting for people understanding the different utilities. Maybe it would be good just to do something.
Someone just on IRC said, could you mute a user called Wade?
Okay.
There was like a lot of feedback. Sorry.
Is it, can you give me a hint?
Yeah.
And then Lay. Oh, Way?
Yeah, Way, yeah.
Okay.
Cool.
Okay, cool. Thanks.
Yeah. I had a question on port numbering that happens when you do the deep kettle show. You do the port numbers that you get and the one OpenFlow assigns the port numbers.
Yes.
So there is like a lot of confusion there. So you just they're not the same, right? So
right. So the question was about the data path port numbers versus the OpenFlow port numbers. So the prior to I think 1.10. We actually created separate data paths, and so the OpenFlow port numbers and the data path port numbers were basically the same. So if you had a port 1 on, in OpenFlow, it was also the data path port number if that was ETH0, for example. The one difference is that in OpenFlow there was there's a local port which is 65534 or something like that, and then that got mapped to port 0. But otherwise, it was a very straight transformation between them, and that was, made things pretty easy. We went with a model we went with this thing called the single data path in 1.10, and what we did was, instead of, so if you created a BR0 and a BR1, in the data path, we actually would create 2 different bridges. And so then you would have, the ports and all that, and, like I just described. For the VXLAN work and for other reasons, we decided that it would work better to have a single data path. And so we have a single data path in the kernel module, and then you have and then in the user space is responsible for keeping track of how to separate the traffic and force that below. And so that OpenFlow local port number is a good example of why we have to change the mapping. So every OpenFlow every OpenFlow data path has this special port number, which is for the local interface. And that maps to 0 all the time before. But obviously that number can't be the same on all of them. And so what we did is we ended up breaking that distinction between that link between the OpenFlow and the data path port numbers. And so now they move independently from each other. And so one of the benefits, the biggest benefit that we saw from going with that single data path model is that we had these patch ports that we would use to connect various bridges. And the performance used to be really bad. So for example, if you wanted to go from a PIF bridge to an integration bridge back to a PIF bridge, that meant that you had 3 different kernel lookups that you had to do. Now what we do is, since we have a single data path, we can actually figure out what would happen to the packets along all of those paths, and then we just have a single flow entry that ends up being a really big performance gain if you have to go through multiple bridges. Okay, so we'll go through a few of the utilities. So OBS OF Kettle is used to speaks OpenFlow, so it actually is an OpenFlow agent. So if you do an add a flow, it actually does the appropriate flow mod OpenFlow message, connects to vSwitch D, sends that OpenFlow message, and does it. So these are some of the commands. So OBS OF Kettle show, you specify the bridge. OpenFlow is configured per bridge. So if you have 3 bridges, then and then you configure them all to talk to the controller, there would be 3 separate OpenFlow connections that all point up to that controller. So this is local to a bridge, so you have to specify what bridge you want for the OpenFlow commands. So, for example, OBS OF Kettle show will show various things about that port, like the ports that about that bridge, like the ports that are attached. OBS OF Kettle dump flow is probably the command you'll use the most, which is to see what the flow table looks like in the switch. You can add flows, delete flows. This Snoop command is sort of interesting. You can run that on the bridge, and then you can actually see the communication happening between the switch and the controller to debug what communication is going on.
What is the difference between OFCTL show and VSTPL show for the bridge?
Yeah.
Is it different versions that I see?
Yeah, so the question was, what's the difference between OBS VS Kettle Show and OBS OF Kettle Show? So OBS OF Kettle Show shows the OpenFlow data for a particular bridge, and so it'll have I can't remember off the top of my head what all the things that it prints out. I don't use it very often, but I think it has like the ports and the port states and like the data path ID and like all of the stuff that's specific to OpenFlow. OBS VS Kettle Show shows the configuration of the switch as a whole. So it'll say like BR0, ETH0 attached, ETH1 attached. It's the database configuration. And so then, so OBS supports standard OpenFlow, and then we've added a number of additional extensions. And actually, a lot of the extensions that we add to OBS end up going into later versions of the OpenFlow protocol, maybe a little bit, maybe with some lessons learned. But so, for example, the older OpenFlow 1.0 and 1.1 had a fixed set of fields that you could match on, and then that was just killing us. So we wanted to be able to match on things like tunnels, and OpenFlow didn't support it, and then you'd have to rebuild. You'd have to actually change the definition of the OpenFlow spec to add anything. So we added this extensible match in OpenFlow 1.2. The ONF who managed the OpenFlow spec, they actually adopted NXM, but they changed it to OXM because NXM stands for Stereo Extensible Match. So OXM is OpenFlow Extensible Match, but it's basically the same thing with a couple of numbers remapped. Registers are being added to OpenFlow 1.5 most likely. Resubmit action gives hardware people great pains, so they're not super excited about taking that, but there are some people that actually are proposing that we add that to OpenFlow. Finding control over multiple controllers so that you could have the controller can you can connect to multiple controllers, and then different controllers can just be allowed to do certain things to the switch. And that I think also got added to later versions of OpenFlow. So we add extensions. They're all open source. They're all in the OVS repo, and then we actually don't push them in the ONF. But usually someone says, oh, that's actually a good feature, I'd like to use it, and so then a lot of the extensions end up getting added. There's something that causes some confusion with people is you have the OVS OFKettle dump flows, which shows the flows that are available for that on that bridge that has been configured. There's a command, this OVS AppKettle bridge dump flows, that shows all the flows that are actually configured on the bridge. So there are flows that can be configured through OpenFlow, and then there are things that can actually be from the controller. So for example, if we have in-band control, which I mentioned earlier, which is that you want to be able to connect you want the switch to be able to contact the controller over an interface that is controlled by the controller. And so you don't want the controller to be able to do something like, put down a flow that says, drop all packets, and then it ends up dropping the connection to the controller, and then the controller can then never change the state. So there are certain rules that we hide from the controller to so that they're hidden from that, so that it can't interfere with those flows. And so the AppKettle bridge dump flows command will actually display those. And the way that we do that is that we use a priority that's higher than OpenFlow allows to define that. So, question on yours? Yeah.
Yeah, we won't get controller stuff, so that's so that, active standby kinds of things, different administrative things.
So there's nothing, like, we don't do any sort of, there's no like role-based control, so everything is sort of cooperative, but the controllers can decide what sort of information they want to see. So like, they could receive notifications when flows get added and deleted, or maybe they only want to see when a port gets added or deleted. And so they're sort of, they're able to control how much information that they see, but we don't have any sort of way of locking down saying that, only this controller is allowed to set it, and then this controller can read it or something like that. So it's more kind of cooperative fine-grained control. But it's
interest or smashing and moving and more and finer control,
I think some people in the ONF, like when that was discussed, had some interest, but I haven't heard that much about it. I mean, I think for like the model that we've used is that the controllers are working sort of together. So you have a control cluster, and you might want to have controllers that are acting as backups, and so they want to have an OpenFlow connection and be notified when it's sort of like high-level events. But you don't want, but they tend to cooperate. Like you don't need, we just haven't had that sort of requirement. I'm not sure exactly how you implement that either. Obviously, I can imagine some mechanisms, but it seems like it could be a little bit difficult. It ends up being a lot of configuration that you would have to do in vSkettle to say to limit the connection.
No, it seems concerned about multiple administrative domains, like provider.
So the model that this is going to be more on the project that I work, that we work on, the commercial project that we do. And so that what we've done there is that we've sort of treated the controllers as trusted, and then there's an API that speaks to the controller, and then that's actually where you would implement the administrative domains. There's one level up, yeah.
So the resubmit action was that you could resubmit a packet from. You said you could simulate multiple tables in a single domain using XML so that you can go to a higher priority flow. in the resubmit action?
So the way the resubmit action works is, you can go to different tables. So this predates having multiple table support, and so this was a way of sort of doing multiple table, but you only had a single table. And so the resubmit action takes as an argument a port, and so what happens is, like let's say the packet came in on port 1, and then you have a flow, and then the action is, you do some set of you fill in some registers, or you do some processing of the packet, and then you do resubmit 4000, and then there would be a flow entry that says ingress port 4000, and then it would have another flow entry. So the resubmit is, gets you back at the table. It doesn't have anything to do with priority, but you end up changing some metadata so that it matches a different packet, or matches a different thing. Sorry, there's a question here. How are registers? Let's see. Okay. Sorry. Okay. So I think the first question was, are bridges retained in CentOS after a reboot? I don't know. Is Guru?
Is something recently on the mailing list on that?
Yeah, I think if Guru is. Oh, there's Guru. Yeah.
How you configure it. If you have directly used OVS vSkettle to populate the bridge, then it will remain through the reboot. But if you're using Red Hat Enterprise Linux configuration scripts, which resides in the network script directory in CentOS disk, in that case, whenever the box is shut down, the bridge is cleaned up, and when the box starts up, it's reconfigured. It's just like a Linux bridge. You create and delete it.
Okay. So
it depends on how you configure it.
Okay. So the answer, if you can hear on the phone, was that it depends on how it was configured. And so if you do it manually with OVS vSkettle commands, it will be persistent. But if you use the configuration scripts that ship as part of RHEL, then, or it's part of the RHEL configuration, then it will blow away the configuration on reboot. And then, so another question: how are registers used in deployments? What are the typical use cases in the field? If we intend to use them in a table, would we store the original content at the table exit? Is there any usage convention? So the way that we've used registers is, the way that we've used registers and the projects that we've seen is, as I mentioned, we have potentially lots of resubmits that we do, and we use it as a scratch space as we work our way through the pipeline. And so we store various bits of information about where we are in the pipeline, things that we saw in the pipeline that might be of interest. I mean, so that's how we've used it. I don't know how other people are using them. And then if we intend to use them in a table, would we restore the original content at table exit? Okay, the registers are just used as they are going through for the processing of a particular packet. So they don't exist past that processing of that individual packet. So, does that make sense? Oh, there was a question about OVS vSkettle show. So here's the output, and so this is information that's in the OpenFlow connection. Here's an example of OVS vSkettle dump flows. So by default, there's just this single entry which matches everything. So you can see that there's actually no match defined, which means that it matches all packets. This is how long the flow existed, 4 seconds. In table 0, there are 8 packets of matches so far for a total of 784 bytes. Idle age means that how long to keep the packet keep the flow until it's ejected. That's set to 0, which means it's permanent. The priority is 0, it's the lowest priority, and then the actions is normal. So this just makes it so that OVS acts as a learning switch, and that's what will happen by default when you start OVS. Just a single flow entry. Okay, and so I mentioned a little bit about hidden flows, that there are certain hidden flows that are not visible to the controller, and we do that by using a very high priority number. So you can't see them for OBS dump flows, so you have to use that app-kettle bridge dump flows command. The kernel data path, there's a OBS dp-kettle command. If you want to look at the data path and hash interfaces, OBS dp-kettle show. If you want to see the flows that are in the data path, OBS dp-kettle dump flows. Sorry?
Okay. In dpctl, whatever command should you create anything else? Is this persistent?
So the question was, are things that are persistent changes that you make to the data path? No, because vSwitchD expects that it's in charge of the cache. So if you do an add flow and vSwitchD is running, it's likely going to see the flow and say, I don't know anything about this flow, and kill that flow. So you can, it doesn't. Add flow is something that's added very recently, and it's not something that's generally useful. So I mean, you could shoot OBS. I think the place where you want to use it if you were testing something in the kernel data path, you just want to kill. I can imagine something like the work that Andy was doing for supporting research. Imagine or research in the kernel. If you wanted to implement something like bonds, you could kill vSwitchD and then just manually configure flows to hash out what the flows look like. You don't want to modify all of vSwitchD, for example. But it's not very useful because if you add a flow, vSwitchD will likely remove it, and then if you delete a flow, vSwitchD will likely populate it the next time the packet comes through. So
big question is, OSCTL connects to vSwitchD or OSD?
OSCTL to vSwitchD, so it speaks open flow.
It is persistent.
Sorry?
And whatever you do with OSCTL is persistent?
No.
The only way you do is the persistent comes into vSCTL.
Right. vSCTL will make changes to the database, which is persistent. OSCTL
and dpctl are transient.
Right, yeah. So if you reboot the box, the flows will be gone when you reboot the box.
So essentially, if you need to do something, you should never use those except debugging.
Oh, well, no. OBS OSCTL you could use, like, you could imagine. I just mean that if you reboot the box, they'll go away. It won't, like OBS dpctl, if you modify it, OBS vSwitchD is just going to do whatever it thinks needs to be done at the data path. OBS OFCTL, if you don't have a controller, I mean, you could end up with the same situation where the controller is monitoring the flow table and say, I don't know anything about this flow table, and shoot it. But that doesn't have anything to do with OBS vSwitchD. But you can run, you could run without a controller. You could have a init script that start up and add a bunch of flows with OBS OFCTL.
But the flow will go away after reboot, right?
Right, but if you had that in your init script, then it would, continue to add them. So they're not persistent across a reboot, but they're not truly transient. They don't go away unless you're doing something.
Is there any difference between OFCTL and vSCTL commands? I mean, is there some?
Well, OFCTL is speaking open flow, so that's flow table configuration. And OBS vSCTL is communicating with the database and is doing like switch level configurations, doing things like adding ports and creating bridges, that sort of thing.
But is the content of the same between what versus what is in the database? Except that what is in the database is persistent.
Well, but the configuration that's in the database doesn't have anything to do with flow tables. It has to do with how you configure the switch at a coarser level, like create BR0 with ETH0 and VIF 1.0 attached or something like that. But it doesn't have anything to do with the forwarding configuration.
When a packet first comes to the user space and the root flow needs to be added, is that added based on the content in the database?
So that
vSwitch C construct the flow for a new packet that
So it's going to be based on the configuration in vSwitchD. So you're going to have, in order for the packet to be processed by vSwitchD, there would have to be some configuration in the DB server that said create this bridge and attach these interfaces. So that has to exist ahead of time, because otherwise, when a packet comes in, you wouldn't know, first of all, if you should listen for that packet, and then second of all, which bridge it would be applied to. So vSwitchD sort of gets the configuration from the the overflow controller or wherever, the flow configuration, and then it gets the database configuration for how it should configure the switch, and then it combines them all together. Make sense? So kernel data path, I think we already talked about that. So here's an example of the OBS dpkettle show command, which is actually sort of interesting. So this could be useful for debugging, especially for performance. As I mentioned, now there's just a single data path since that change that we made. So when you run OBS dpkettle show, you'll only see this system and OBS system data path. Before 1.10, you would see like a VR0 or a VR1, however many bridges that are configured. Now they all get compiled down into this one data path. So there's a big line. This is a cache. So the number of, this is the hit count. So that means how many times the packet came in and it was found in the kernel cache. Miss means that it was an entry wasn't found and it got sent up to vSwitch. Lost means that the queue of packets that are being sent to vSwitch for processing overflowed, and when that overflows, then the packets get lost. And so in this case, every packet that was received by vSwitch was ended up being processed. There were no lost packets. There are two flows in the kernel, or in the flow table in the kernel. Masks, this is where we're talking about the number of masks, these are stats on that. So right now, this is a simple flow table, so there's just one mega flow type, of a set of fields that are being matched. So there are that many hits. And then these are the different ports. So you can see there's this is an internal port, the VR0. So there's a VR0, and there is no VR1. There's just one bridge here. And so imagine that ETH0 and ETH1 are both likelihood just attached to this VR0 device. But this is the data path port version we were talking about before. Any questions on that?
So, what I'm confused about is to move the real ETH0, which is a real NIC card, and put it under the bridge. How does it exactly work? I mean, in the sense, what happens to pull that NIC out and put it as under VR0?
So, in the kernel, there is a on the netdev that describes ETH0, it talks about, it has a thing that references the bridge that it's attached to, and so whether that's a standard Linux bridge or an OBS bridge, but there's basically a identifier so that if that's populated, it knows that it needs to be processed by a bridge. All right, so OBS dpkettle dump flows. So before, as I mentioned, there was that they used to be exact match. So you can see that in this case there is there's the TTL that we discussed. So we always match on everything. This is a ping packet that's running between two systems, or a ping session. And so then with mega flows, we started these things. So the policy ended up, this is just a simple L2 learning switch. So before these would have, if someone then did then decided to telnet to port 23, then there would be another flow entry. But with mega flows, these things are wildcarded. You can see these /0s. So if someone ended up telnetting to the other host, the telnet session would end up matching this flow entry where it wouldn't have before. This output is a little bit old. We're working on cleaning it up. So like in this case, where the entire IPv4 header is, the ICMP header, everything is wildcarded. You just wouldn't see ICMP anymore because it's wildcarded. So the output's just been cleaned up a little bit in later versions, and we're continuing to improve that. OBS kettle is a this is where we saw that the thing where we were dumping the hidden flows. This is that runtime control facility that we have just this sort of generic that communicate with OVS daemons. So you can run, if you run OVS apphettle and then tell it to connect to vSwitch D and run help, it'll show you all of the commands that are available through apphettle. And so that would have like bridge dump flows or change the logging level. If you ran the same thing with this -t target and you specified OVS DB server and you ran help, it would list the ones that are specific to that. So also logging level and, for example, compact database. Version is actually something that's fairly helpful. We've run into problems before where this will tell you the version of the daemon as it's running now. Like we've run into issues where we had a bug and someone said, oh yeah, no, we're definitely running the more updated version, but you can't really tell just by the process, and so you can actually see what's running the version. vlog list specifies all the different logging modules and shows what the configuration level, so you can, and then vlog set allows you to change that so that you can start debugging higher or lower for a particular module. And then we describe all of the features in OVS apphettle. They should be in the man page of the target. So vSwitch D will have a section that describes, these are all the commands that are apphettle commands.
This is a point and awesome.
Is there a question on the phone?
This is
that sounds like background noise.
Okay, thanks. All right, so why don't we just do this? Why don't we just do a couple more slides and then we'll call the session. So I won't go into a lot of detail here, but just it's sort of an interesting or a useful utility. Some of the flow tables can be very complex when you're dealing with them. With you add them through OpenFlow, and then knowing how what's going to happen to a particular packet can be difficult. So this is just a simple flow table that I added.
Okay. So this
there's a OF-proto trace command, which is one of those OVS apphettle. And so if you run OVS apphettle OF-proto trace, and then you give it a packet that was received in the kernel data path, you can see how the packet was processed. So this packet, because it came in on port 2, that's attached to BR0, and then we show this is what the flow looked like at this point in the processing. This is the rule that we matched, and then the action is normal, and then you can see what we decided to do with the packet. And and so like I mentioned, we have. I've seen flow tables where there are hundreds of thousands of entries. It'd be very difficult to figure out what what actually happened to this particular, to a particular packet. And so, if you have lots of resubmits and going to different tables, this can be very long. But you can see about how exactly the OVS vSwitch D decided to do what it did with that packet. So here's an example. And these slides are the OpenStack slides that I did in Hong Kong end of last year, and they're available on the Open vSwitch website and under the documentation tab. So if you want to dig into this more, all these slides are available. And then logging, last thing we'll talk about. That apphettle is what you use to configure the log. By default, if you don't specify a target, it'll do vSwitch D. So you do -t if you wanted to look at the logging for OVS DB server, for example. Default log level is info, and so if you wanted to really dig into the details, you can configure it with the debug with the apphettle vlog set command. So here's OVS apphettle vlog list, which is going to show all the logging modules configured for vSwitch D, and so you can see that here are the different modules, and this is the configuration for outputting to the console, to the syslog daemon, and to the file. And then here's an example where we run apphettle vlog set, and we're setting the OF-proto module file to debug. And the log files are typically, I mean, this is configurable, but by default, they're usually in var log open vSwitch. And so vSwitch-Ds is obsvSwitch-D.log, obsdb server is obsdb server.log. We have some other daemons that are, similarly named. And then usually the configuration database is an etsy open vSwitch conf.db, and you need to know the location if you wanted to play back that log that shows all the configuration that happened in obsdb. That's the command that or that's where the file exists that you can dump out the logs. Okay. That's all slides I have.
Great. Any last questions? So it's 11:36. We should probably break for lunch here for folks that are here. For the folks that are remote, I'm going to take like a half-hour lunch break. We'll come back. In the other room, we have a list of topics for under things like documentation, discussion, programming things. What we're going to do is we're going to start breaking out into groups where people are going to go grab topics and break out into rooms. We'll set up IRC channels for those for the remote people, so that and we'll put those on the main Open vSwitch IRC so that they know what IRC channels to break out into if they're interested in a particular topic. They can subscribe to that IRC channel. So how about a little after 12, like we'll say 12:05, we'll regroup and after lunch and start again. Sound good? All right. Thanks, Justin. Bud.
Sorry.